Hello, welcome to the third installment of the acid-base equilibria series. Now, once again, important to pay attention to this because it shows up on the AP exam a lot. So in this particular video, we're going to be looking at weak acids and bases and then how to solve for them, how to interpret them. Now, the nice thing about it is you're really not adding any new things to your learning. You're just sort of taking some of the stuff that we have already learned and applying it to acids and bases. And so because acids and bases are so important in our physical world, there's a whole lot to do with them. And so we need to be able to understand how to work with them. All right, so when you look at a weak acid or a weak base, it's just like a weak electrolyte. And so the idea is that it doesn't fully dissociate. So we have this equilibrium expression in here, which means that not every single hydrofluoric acid molecule is going to donate a proton to the water and become a fluorine ion. Not every single one. Only a certain amount will. And so we have a weak acid because at some point it's going to donate as many as it possibly can, and then it's going to start flowing back in this direction. So we're going to have an equilibrium going on. So an equilibrium expression for acids we call a Ka. So we call this a Ka because it's the what is called the let's see, what is it called? Acid ionization constant. And then we also have a base ionization constant. So an acid ionization constant, of course, is only necessary for weak acids because weak acids would create an equilibrium, whereas strong acids, you just have a big arrow here. It would go to completion. And whatever you put in on this side is going to end up as completely one-to-one ratio of hydrogen ions donated to the water. But for weak acids, we're going to end up with an equilibrium constant expression. And so it's called the acid ionization constant, Ka. And so the acid ionization constant is no different than any old KEQ that we would have written for anything else, and so the concentration of the products divided by the concentration of the reactant. So you see here we have the hydronium and the fluorine ion divided by the original hydrofluoric acid, and we do not include the water because the water is a pure liquid, and you never include pure liquids or solids in your equilibrium constant expressions. Now, if we had some coefficients in the balanced equation, we of course would bring those up here and put those as exponents, but we do not. So we find out that the acid ionization constant for hydrofluoric acid is 6.8 times 10 to the negative fourth. Okay, so what do we do with that? Well, one of the things you can do with that is you can quickly compare the Ka of one particular acid to the Ka of another particular weak acid, and you could tell which one is going to be stronger in the sense of which weak acid is stronger. And so we look here, this one, the Ka for carbonic acid ends up to be 4.3 times 10 to the negative seventh, so it's a smaller number than this, and that smaller number indicates that these products are smaller in ratio or in respect to their original reactant. Okay, and so then these products are going to be greater in respect to their original reactant. And so the idea here is that we're going to have a greater amount of hydronium ions with hydrofluoric acid than we will with carbonic acid, meaning that this is going to have a lower pH than this one. So Ka gives us a quick way to analyze, it's just sort of a general idea of which weak acid is going to be stronger than another. All right, and if we look at weak bases, here, let's put this up here, weak bases. All right, so a weak base is really similar. There's not much different about it. And here we have ammonia. Now, when ammonia goes into water, it pulls one of the hydrogen ions away from the water, creating a hydroxide ion. And whenever you pull a hydrogen ion to yourself, Bronsted-Lowry says you are a base, and if you donate one, you're an acid. So in this case, the ammonia pulls one to itself, creating the ammonium ion. Okay, so when we look at the equilibrium constant expression, or the base ionization constant, I should say, that's what this is. The Kb is the base ionization constant. We see we have the concentration of hydroxide ions times the concentration of the this is ammonium divided by the ammonia. And so the products divided by the reactants. And so our Kb is 1.8 times 10 to the negative fifth. Now, if we're quickly to compare that to, for example, a hydrogen carbonate ion. So the hydrogen carbonate ion can turn into an acid. And if you just put hydrogen carbonate in the water, it may take some of those hydrogens for itself, create some hydroxides. So we clearly have a base here, and end up with this H2CO3 right here. And so here's our base ionization constant. We have the products over the reactants, and you'll notice that this is a pretty small number. So this doesn't really happen very much. And actually, if you analyzed it back the other way, it would be a little bit more. So we would actually find out that this would contribute more to making acid than it would base. But that's why this particular ion makes a good buffer, which we'll talk about later. But in quick comparison, you can see that clearly ammonia is a stronger weak base than the hydrogen carbonate ion. All right. One of the things that pops up a lot on the AP exam is calculations with weak acids. So let's go ahead and do one of those real quick. And so here's the question. If I had a 0.2 molar solution of acetic acid, and acetic acid is a weak acid, we know that because it has a Ka. And it's also not one of our strong acids that we memorized. And one of the easiest ways to determine if it's a weak acid is you have those strong acids memorized, and this is clearly not one of them. Okay, so we take this, so we put our products over our reactants. We know what our Ka is, and so the question is, what is the pH? So you often will get these questions as if I put this original molarity of the solution, and here's my Ka, what's my resulting pH going to be? So the pH is going to be the negative log of the hydronium ion concentration. So pH equals the negative log of the concentration of the hydronium ion. So we have to figure out the concentration of this hydronium ion from the Ka. So this is similar to your equilibrium constant expressions where you had to do this. Given an initial amount and your KEQ, you can solve. You just have to do the ICE table and plug in the numbers. And there's a few little modifications to it, but not much. Okay, so let's go ahead and put our ICE table down here in order to solve for our factors. So we're going to have our acetic acid as our reactant here, and none of these are solid, so they're all going to be in the ICE table as well as in the base ionization constant expression, or this is acid ionization constant expression, sorry about that. And so we find out that we have a 0.2 molar initial concentration. So let me go like this, 0.2 molar, and that's going to be minus x because the balanced equation shows us here a factor of 1. So this one is going to be, here, let me add that in there. This one is going to be plus x, or actually these are initial concentrations, sorry, I should just not get ahead of myself, 0 and 0. So my change here is going to be, that's what I did, I put my change up there, is 0.20 molar minus x, and this is going to be plus x, and this is going to be plus x. All right, so as far as equilibrium goes, in order to solve for x, what we can do is we can take the Ka and plug it in. So here's our equilibrium constant expression, and so our Ka, now instead of writing Ka, I'm just going to write what it is. So the value of it is 1.8 times 10 to the negative fifth. So we learned that up here, and so I'm going to take that down, I'm going to insert that in for my Ka, and I'm going to substitute in my factors from my ICE table in order to solve for x. And so on top, we're going to have x, and so that ends up x squared. On bottom, we're going to have the initial concentration of 0.2 molar minus x. Now, one of the things that we do in acid-base equilibria is when we're at this particular point, the value of x, you're going to find this out once we get done calculus, the value of x is going to be really, really small. And so actually for calculation purposes, subtracting it from this won't even alter the answer. So to save some time and to just do it more quickly, we're going to, well, I guess that's the same thing. We're going to just get rid of it. And so you can do that. When you're doing these calculations like that, you can actually just remove it, because it's almost always insignificant compared with the initial concentration of acid. So we just use the initial concentration in the bottom of this equation. And I wrote it in there to begin with just so you could see that we do know it should be there, but we do have a reason for not needing to use it. And so, that, of course, that simplifies things. So you're going to take this 1.8 times 10 to the negative fifth. You're going to multiply it by 0.2. And then you're going to take the square root of that. And you're going to get this. You're going to get x equals 1.9 times 10 to the negative third. And so that's the value of x. Now we find out that H3O is just simply an x, so then that's also the concentration of the hydronium ion right there. So now all we got to do is take the negative log of that, and when we take the negative log of that, we find out that we end up with a pH of 2.7. So that's our pH. For this particular thing, if you are to throw in an initial concentration of 0.2 molar acetic acid, it will dissociate, producing some hydronium ion concentration, and that hydronium ion concentration is going to end up calculating out to exactly a pH of 2.7. So given any initial amount, you can calculate for pH using the ice table and the acid ionization constant expression, as well as a base ionization constant. You could use either one in order to solve for the pH using a weak acid. So hopefully that helps. And like I said, there's a lot of problems on the AP exam that want you to do this, specifically with weak acids and weak bases. So we've got to pay really close attention to this one.